All right, so I think it's time for our next guest. So James Arthur, are you there?
Hello, can you hear me?
Hello, James. I can hear you and loving your top hat there.
Thank you. Good morning.
Good morning, good afternoon. So was it like, wait, what time is it where you are? 5:30 in the morning?
It's way too early.
So
here we are.
Yeah, here in Australia, we're all good. It's 1:30 p.m. on the west coast of Australia. So I am bright and awake, and I am very impressed that you are awake at that crazy time in the morning. So
I don't know how I did
it. Yeah, is that right that you're a student?
I'm a
So
student
where
and
are you
mathematical
studying
communicator. I'm studying at the University of Exeter.
Okay. All right. So it's not known for students to be up at 5:30 in the morning. So extra kudos to you for being here at this crazy time. And yeah, so you're a mathematical communicator. Apparently you've been on the radio. Tell us a bit about that.
I've been on BBC Radio 5. I go on pretty regularly. I talk about current affairs under a mathematical lens.
So I guess you've had a lot to talk about at the moment with COVID.
Oh yes, we've had plenty of stats stories coming along. It's always good fun. I enjoy the stats. I enjoy the numbers.
Yeah, that's fantastic. So maybe taking a break from the dark world that we find ourselves in, why don't you brighten our Saturday morning with a bit of magic? What are you going to talk to us about today?
Right. I've got a couple of slides prepared if I can remember which button it is. Is it that one? No, it's this one. There we are. I can never remember which buttons that are the ones I want to talk about. I'm seeing a slide
called Magical Addition.
Yeah,
so
brilliant.
Pretty excited about that. So I see you've got your Twitter handle on there as well. So yes. If anyone wants to follow you, and your website has the same name, that's right, isn't it?
Yes, everything. I'm Left James A everywhere. Just type www.leftjamesa.com or put that in Twitter. You'll find me. I'm all over the place. Too much.
There's no too much. All right, so take us through your magic trick.
Right. I'm going to start off with something pretty easy. We can add numbers. So we can say that 3 plus 2 is 5 and 2 plus 3 is also 5. And we can do that with other numbers as well. We can do that with fractions and whole numbers like 1.5. We can add 1.5 and we can add them with 1/1 and ½ second, then ½ and 1 second. And after that, we can kind of say, after a slight calculation, everybody should be able to say, okay, 1.5 can be added both ways and they're the same thing. We call this fact commutativity in maths. I'm going to be using that word quite a bit. So I just thought I'd add this in. These are kind of prerequisites to my trick because there's a lot of maths going on here. And we can look at fractions. So we can have any two counting numbers. Either they're normal numbers, you can write them 1/2, 3/4, or even pi over e if you're so inclined. But I'm going to primarily talk about unit fractions. And by this, I mean there's a 1 on top. So 1/2, 1/37, or 1/pi. And as we saw before, we can do the same thing. We can add them. So 1/2 plus 1/3 is 1/3 plus 1/2, which is 5/6. I think I've done the maths correctly. And now we can do something funny with them. So what we're going to do is we're going to take all the unit fractions. And we're just going to add them all together. And at this point, I'm going to try preempting chat by saying that this is not a -1/12. I know the comment is coming. I know it will be there. And yes, it could be -1/12. We're going to call this infinity for the moment. And
I believe that there was a magic trick maybe a couple of hours ago about the -1/12 thing. So if you do want to watch that back, that's all been pre-recorded, and you can go to the website and have a look at that. And also just to say to people that please don't put any spoilers into the YouTube chat. So if you've already seen this before and you know what's going on, you can sit there feeling smug, but don't type anything into the chat window that might ruin it for anyone else.
Also, a normal number is I want to say natural, but then there's a few issues there because we don't know a natural not including 0. So that's what I'm going to class a normal number as, because I was looking in the chat and there's someone that wants that. So if we take all the natural numbers, not including 0 or if you don't include 0 in the natural numbers, ignore that second condition, and we add them all together, we get that it diverges, which means it doesn't equal anything, it blows off to infinity. The simple proof of this are my 4 graphs, which I think you can see. You have the first iteration, which is just a line, 10 iterations, which turns into something a bit like natural logarithm. And my proof for this is that the 100 iterations looks a lot like the 1,000 iterations, and the 1,000 iterations isn't a right angle, and we'll see later something more like a right angle. So now we're going to do the same thing, but instead of adding the even fractions or even unit fractions, we're going to subtract them. So instead of doing 1 plus a third plus a quarter plus a fifth plus a sixth, we're going to go 1 negative a half plus a third negative a quarter plus a fifth negative a sixth. And surprisingly, this converges, right? This converges to a number which is about 0.69, which is natural logarithm of 2 to mathematicians. And at this point, I'm going to ask the audience to come up with a number, a small number, I'd say something less than 5, and probably something you'd think was hard to calculate. And I'm going to leave these slides for the moment because I think the next slide gives away the trick. Does it? No, I don't think it does. No, it doesn't. I haven't got that slide. We never did that slide. That's fine. So we can.
So yeah, so just to confirm then, so you're wanting the audience to think of a number that's less than 5 that might be hard to calculate. Is that what you said?
Yes.
I'm not quite sure what it means hard to calculate. I don't know what the context is for that. So maybe not an integer, not a whole number.
Yeah, basically not an integer, not a whole number, a number that probably maybe it may have an infinite number of terms or number of digits. It may be rational, a number that you wouldn't say is easy to write down on a piece of paper.
And yet we have to be able to write it down to tell you what it is, the number that we're thinking of. So
give me a name of a number or the first couple of digits of this number, and then I'm probably going to be able to extrapolate what the rest of the number you want. Or give me something to tell me about this number.
So I can see that there are some suggestions coming in on the YouTube chat. So most people are kind of doing variations on things with pi and e. So we've got pi to the power e over 3, or pi times 1.5. Are these the sort of numbers that you're interested in?
Yes, these are numbers that I want. I will keep these. I've got the chat open on my side monitor down here, and I will use them in a minute.
Okay, so you don't need to keep them secret. It's not like we're thinking of a number.
No, don't keep. Sorry, yes, don't keep them secret because they're useful for me more than anybody else. Okay. And you'll see why in about 10 minutes.
Specific one?
Yeah, you can, but keep it in mind. I don't want it just yet. I was asking in preemptiveness of something I'm going to do later. So if we move to that one, and you should. I'm going to move this out of the way because you can see my second screen. I'm going to move you over there so we keep an eye on the chat. So I've got some cards here, as any good mathematician should have. And these have just got the unit fractions. So we can say 1, a half, a third, a quarter, you see that, just about a fifth, and so on. And these numbers may look familiar to you. They're the ones we've just seen in the slides, and they have colouring. This colouring is important because we see the even unit fractions are blue, and in our sum before we subtract them. So if you see blue, that means subtract. If you see red, it means add. So I'm going to tell you, as we saw before, that this sum here is 0.69. If we kind of carry on, I've got some more cards, but you can carry on putting down the cards and you can carry on adding, and eventually you'll get to the natural logarithm of 2, which is 0.69. I'm now going to take the cards back, and I'm going to do something slightly different with them. if I say I'm not going to say something completely and utterly wild, because, yeah, we saw earlier that for two numbers, 1 and 2, 1 plus 2 is equal to 2 plus 1, which is equal to 3. I'm now going to blow your mind. That isn't true. Well, not for all numbers. That's not a general rule. You can't take any two numbers, A and B, and say A plus B is B plus A. And this is why.
That will be impressive if you can show us that, because that's something that I've believed for my whole life.
Well, you better get your mind blown. We're going to go.
I'm ready for it. Lay it on me.
And then we're going to subtract a half. And now we're going to add a third. And we're going to add a fifth. So what we've got here is 1. Then we go down to a half. Then we got to about 0.8. Then we go above 1. And now if I can find the right card, we're going to go down to we're going to go negative a sixth. So that's 1 negative sixth, which is about 0.8, I believe. And then I've got to put a seventh there, which takes it back up to 0.9, and a ninth, which juts over juts over 1. And then we put an eighth. And then I've run out of red cards. But if we carry on doing this so that we go below the number we want and above and below and above and below and above, you'll get to a point where you have that number. Because the numbers get smaller and smaller and you're encroaching in and in, this sum, if you carry on with it, where's my answer 1 card, and so on, that is 1. But we just said all these numbers.
I feel like I need some clarification about how you're putting the numbers down. Because, for example, I see that a quarter is missing at the moment. So are you saying that a quarter will appear somewhere? How do you decide what's the next number to put down?
Oops. I've messed this up a bit horrifically.
Okay.
I was like, I looked at the cards. Cards were in order. Yeah, that was my fault. Yeah, sorry.
Okay.
That was not supposed to be a sixth. That was supposed to be a quarter. But my cards got out of order, and then I was like, oh, okay. Sorry, yes.
But you're not. But I see still that you're not putting the cards down in numerical order. You've switched the order around. So how do you decide which number comes next?
Can I leave that for a moment? Can I leave that to stew in people's minds?
You want us to try and figure it out ourselves? How do we work out the next?
Yes, I've given you a skeleton explanation of what's going on, but I think it would be good if people understand what's going on here, because this is the trick. What you're doing here is the crux of what the maths is fiddling about with, because you're going, basically what you're doing is you're taking some numbers up to a number. If I do, let's have a look. You take some numbers going up to a number, and then you say, okay, I have this said number. And, I know, it's in my slides. We have this, there we go. If you look at this slide here, I think I'm showing
I'm still seeing the document camera.
How are you? That one, that one, that one, that one.
There we go. Yeah.
That one there. Here's my slides. And we saw this slide before. We've got these graphs. So I didn't put particular emphasis on what's going on in these graphs. We'll go back to them. You can see here that there's a very uppy, downy motion. And if you look at kind of higher tolerances, look at the half tolerance, which is the first graph. You're going down, up only once. Then again, in the half, you're going down, up, down, up, down, up, down, up. And you can see, if you look at the tolerances, you have shorter and shorter downs and ups. So when you get to the point like a 0.01, which is a bit nuts, you can see it's basically a right angle, which means that it's converged to 0.69. And I can do the same for, if I do this, I'm fiddling with tech, but I can do the same for any number. This is why I asked for the number earlier. You can see some Python here, hopefully.
Yes.
And brilliant. And we just had 1. And if we go at 0.1 tolerance, as we saw before, it's a right angle. So that converges. Can you see the graph? I'm not.
Yes, I can see the graph. I'm just wondering if you can
It's
explain what it means to have a 0.1 tolerance. What does that mean?
Okay. Yes, that's the thing in my code. A 0.01 tolerance means that when I'm adding and subtracting numbers, it stops when it gets within 0.01 of my target number. So my target number here is 1. My tolerance number is 0.01. And I want to get within 0.01 of 1. And it's basically just a code thing. It's basically to say, don't carry on going until you get to the actual number, get close enough, because I don't want my code running for an infinite amount of time.
So is this when we see the downs and the ups on the graph, that the amount it goes up and down is now becoming less than 0.1?
Yes. So if we have, it's basically the endpoints of these graphs are, well, the endpoints, the spiky bits, they are discrete points in a sequence. And what I'm doing here mathematically is taking a limit of a sequence, but they're points. And if one of these endpoints or pointy bits gets within 0.1, or no, it's now 0.1, it used to be 0.01. If it gets within 0.01 of 1, then the code stops. It's basically just a fail-safe to say, okay, if you can't converge, stop within 0.1 or 0.01. But if you can, stop within, it's a thing to stop the code from going a bit haywire, basically. But I could carry on running this until we actually reached 1. You can see I've got a number up here that we actually reached 0.9900129276989882. So we got within 0.01 of our target number, which is 1.
Okay,
Hopefully
so I feel like there's
a
going to
better
be some
explanation.
actual magic coming up. You're going to do something with those numbers that the audience gave us earlier.
Yes. And I couldn't know any of the numbers that the audience put in the chat. And you have a number for me. Hopefully it's an easy one to put in Python.
I wrote down the square root of e times pi. Now, actually, I need to get my calculator out to make sure that's a number that's the right size for you.
I don't know. E is 2.9.
Yeah, about 2.9 something.
2.91. We'll go for 2.91 and we'll go with 3.14. We're doing live Python. Oh, we love live Python.
You're a braver man than me.
I know I am. Right, so if we go pi times, yeah, sorry, let's go 1. Let's start with the tolerance for half. See if it converges at half. Yeah, it converges at half. The square root of pi plus e is approximately 3.022. Are you seeing my Python?
No, you've
you're
stopped
not.
sharing.
That's because I was typing in numbers. So,
okay.
Oh, it's 0.3. It's ended up there. Right, so this is our, for 0.5 tolerance, we've got a curve. That's interesting. Mainly probably because you're adding, yeah, that makes sense, because you're adding positive or odd unit fractions. So you're adding 1, a third, and a fifth. I don't know where the fifth is on there. So then that creates that curvy nature. And to see if it converges at 0.25. Yes, it converges at 0.25. And does it converge at 0.1? Yes, it converges at 0.1. And does it converge at 0.1? Hey, we've just taken all the numbers that we saw before. We've taken all the numbers between all the unit fractions actually, and we've done basically, because we've got that then plus a quarter, plus a fifth, plus a sixth, plus a seventh, plus an eighth. What's an eighth? I've lost an eighth there. Plus ninth and so on.
So if I can confirm this crazy done, you've taken all the unit fractions and you have added them up in some order, and the answer has been the square root of e times pi.
Not exactly. I've added all the, I've taken all the even unit fractions are negative. So this half is a negative half because it's blue. And this quarter is a negative quarter, but you can't see it because my head is in the way. This is a negative quarter. I haven't got negatives on there, but I can probably add them. So this is a negative quarter, a negative half, that's a negative quarter, that's a negative 6, that's a negative 8. So the sum you're doing here to begin with is 1 plus a third, then plus a fifth, and plus a seventh, and plus a ninth, and so on. And what I've just done is I've rearranged these terms. So in some order, I can't tell you what that order is, but I can tell you that the order for the for 1 is this. If I rearrange them to that, quarter, then a seventh, then a ninth, then a negative 8, and so on. That order, oh, you can't see that, is 1. And some other order is a half. And some other order is square root of e times pi. So I've just broken commutativity to a great degree because I can call all these terms past 1 number. And I can call that another number. And or choose a term and call it another number. And a plus b is not equal to b plus a because I can move, say this is my number, I can move this number to be there. And now I have a completely different number.
My mind is definitely being blown at this moment because, yeah, that's not what I learnt in primary school. If you change the order that you add up numbers, the answer shouldn't change. And you're telling me that it does. And presumably it's because you've got infinitely many things in your summation there, that infinity is playing weird tricks on us.
As usual, the trick is infinity. But I think this is rather neat. I really quite like this. This is one of my go-to party tricks, which is like, commutativity does work. And it's like, yay, I love commutativity not working.
It is pretty mind-blowing. So if the audience who are listening in want to know more about this trick, what should they search for? What should they Google to find out more about this?
This is called the Riemann rearrangement theorem. So this is a complete another thing. Riemann came up with this one night in his attic, I'd like to believe. He was sitting there in his dusty attic during Halloween, adding weird and wonderful unit fractions. And he thought, oh, this doesn't work. I can make 1 out of these unit fractions. That's cool. Probably the intuition came from the graph rather than the numbers. He probably plotted the graphs we saw and then said, oh, okay, I can make this into a different number. And
so we've got some good questions in the chat at the moment. So one person is asking, does this only work for telescoping series? So this idea that some of the numbers are plus and some of them are minus, is that part of what makes this work?
I think it only works for these numbers. No, it works for series that have, get myself confused. It only works if you have a series with a -1 to the, if you have the nth term of the series, it has -1 to the n at the start. So that means every other term is a negative term. So you always need the same number of negative terms as you do positive terms.
Yeah, although the same number in infinite terms is always going to be a weird thing. But you're saying if they alternate, then you
if they alternate, yes.
Yeah.
If it alternates, you can do this with it. If it's an alternating series, it works. I don't think it's, I've got to recall the definition of telescoping. It's way too early to do that.
Yeah, so what is it now? Like 6 o'clock in the morning there? So you made it through.
It's 5 to 6.
Yeah.
And I'm getting some so weird. I was looking forward to someone saying, that's weird. And I'm like, yes, that's the best thing you can get out of this trick.
It is very, very weird.
That's very weird. And I'm, yes, it is very weird. It's completely nutty weird. But that's what you get with this trick. It's some weird number things that go a bit weird. I think the moral of the story is numbers go weird at infinity.
So do you think that you became a mathematics student because you saw weird things and you wanted to understand how they work, or you've discovered weird things since you became a mathematics student?
I think that it's mainly I was interested by the weird. I was like, okay, why doesn't I was always kind of fiddling with numbers in my head, and I was like, why doesn't this work? And I never had the skills to prove it. And I was like, I was annoyed that I couldn't do that. So my main motivation is to just explain the weird and wonderful things that are going on in the world, and to kind of, yeah, that's what I use maths for. Things like
Fantastic.
this, like what on earth is going on.
Yeah, I think there's something that I learned about when I was a student, but unless you've done the serious maths degree, this is the kind of amazing result that you won't be coming across in casual conversation in your local cafe. So really wonderful to have you on the show today to tell us about that, raise a bit of infinity maths awareness with us. So we've got about 3 minutes left. In the last 3 minutes, is there anything else you want to talk about, a treat that you've brought along, or anything else you want to talk about?
My treat was basically going to be going through any more suggestions. If anyone wants to chuck any more numbers in the chat, and we can do a couple more of them. That was my treat. The code was a treat, to be perfectly honest. But because people like Python, well, I like Python code. Python has been the bane of my life for the past 3 years. But still, I finally got to grips with it. And now I'm like, Python is amazing. I can just write little scripts and off we go. And this was one of my little scripts I wrote last year. And I was like, okay, this is fun. Because when I was thinking about this talk, I was like, ooh, I can do Riemann rearrangements.
Yeah, I think coding is one of those things that makes you feel like a bit of a wizard, right? Like you do some magic and then the right answer comes out of this machine. So that's really great. So just looking at what's happening in the YouTube chat. So someone has copied some stuff off Wikipedia. It's obviously gone away, looked up the Riemann series theorem. So a bit of information there for anyone who is interested. So
you are correct, Andrew.
Discussion happening around that trick.
You can steer the sum to any arbitrary. Yeah, that's basically what I'm doing, is I'm steering the sum to any value I want by just adding and subtracting numbers. That's what I'm doing.
Yeah. All right. Well, thank you so much, James, for coming on the show today. It's been really great to have you here. We've got a couple of minutes before we're going to be passing over to the next math magician and the next presenter. So
you'll be seeing me later on again. I am hosting at approximately 3 o'clock, I believe, but I will be
3 p.m. UK time.
Yeah, 3 p.m. UK time.
Okay, so it's now 6 a.m. So I've got to get this in my head, because at the moment it's 2 p.m. here in Australia on the West Coast. It is 6 a.m. GMT over in the UK.
It is 6 a.m. GMT.
And the show is going to be going on until 9 p.m.
Correct.
So hang on. So if it's 6 a.m. now and we're going until 9 p.m., how many hours is that?
15 hours.
15 hours to go.
I may be brutally... No, 50. What am I on about?
Hang on, 6 a.m., 9 o'clock. 9 o'clock is...
No, I am correct. 15.
21 o'clock. 15, yeah, I think 15.
Yeah, 15. I am correct. My mental arithmetic was going
How many mathematicians does it take to do mental arithmetic?
I can't do it.
So there's 15 hours of the 24-hour Maths and Magic show still to go.
I've got a lot to catch up.
So every half an hour there is going to be a new presenter coming on to show you a magic trick. Everything is being live streamed on YouTube. It will be recorded for anyone not able to watch it live now. So if you're watching it live but your friends and family can't join at this moment, they can always watch it back later. So do tell everyone who's interested in maths or magic all about the show, and get them to come along to the YouTube channel and check us out. All right, so thank you very much, James. I'm going to say goodbye to you now. It's been lovely to have you on. All the best with the rest of your studies and your career.
Goodbye.
Thanks.